Hello everyone, my name is Changkun Ye, a PhD student at the Australian National University. In this video, I would like to introduce our CVPR accepted paper, Open Set Label Shift with Test Time Out of Distribution Reference. This is a work collaborated with Dr. Russell Tsuchida, Dr. Lars Peterson, and Professor Nick Behrens. To begin with, I would like to give you a brief introduction about the label shift problem. What is label shift and why we care? Nowadays, deploying a deep learning model, usually a deep neural network model, in the real world usually face the problem of distribution shift. In particular, when the trained data distribution is very different from the test data distribution, the deep learning model trained on the training data can yield unsatisfied performance on the test data due to the shifted data distribution. Label shift is a particular type of distribution shift where the label distribution is difference between the source and the target domain. An example of the label shift problem is the closed set label shift problem. In this case, the source domain trained data and the target domain test data share the same set of classes, and the label distribution is shifted between the training and the test data. Also, to ensure that we are only discuss the label distribution shift instead of other type of distribution shift or the mixture of distribution shift, it is usually assumed that the conditional distribution of image given label is invariant between the training and the test data. Examples of the closed set label shift problem includes class imbalance problem and long tail recognition problems. In these two problems, the source domain usually have a highly imbalanced or even long-tailed label distribution, and the target domain have a close to uniform label distribution. This work considers a more challenging open set label shift problem. In the open set label shift problem, the target domain not only have the classes that appear in the source domain, it also contains samples from an extra out-of-distribution class. Also, we have the label distribution between the source and target domain are shifted, and the conditional distribution of image given label is invariant. Example of the open set label shift problem is open long tail recognition problem, where we have the long tail label distribution in the source domain and the uniform label distribution in the target domain. In the open set label shift problem, we are given with the assumption of conditional distribution being invariant, and also we are given with source domain labeled data, source domain classifier, and unlabeled data in the target domain. Our objective is to obtain an optimal classifier on the target domain. Three sub-problems usually appears in the open set label shift. Firstly, we want to make sure if label shift happens, that is the open set label shift detection problem. If we found the label shift is different, the label distribution is the same between the source and target domain, then we may not need to adjust the classifier. Secondly, if we found the label distribution is different, then we want to estimate the target domain label distribution. And finally, after obtaining an estimate of the target domain label distribution, we want to adjust the classifier on the source domain to the target domain based on the estimation result. The open set label shift estimation and correction task are our focus in this paper. The main difficulties we are facing in the open set label shift problem are twofold. Firstly, all the distribution data in the target domain have to be considered with an extra out-of-distribution detection model, where the out-of-distribution detectors have been proposed in a lot of OOD detection literatures in previous works. Secondly, only one existing open set label shift models have been proposed, which requires the retraining the classifier and the ID versus OOD classifier entirely. That means a lot of computational overhead, which we want to avoid. In this work, we proposed a novel open set label shift estimation and correction model that having these following advantages. First, our model does not require fine-tuning or retraining, which is feasible for large neural network models. Secondly, our model is designed to be feasible for any proposed ID-OD classifier, so that the OD detectors proposed in the previous out-of-distribution detection literatures can be used in our model. Finally, under reasonable assumptions, our model is guaranteed to obtain a maximized likelihood estimate of the target label distribution, which provides theoretical guarantees. The general idea of our model is the problem reduction. If we can rewrite the open set label shift problem in a mathematical form similar to the closed set label shift problem, then we can utilizing the advance in the closed set label shift problem to tackling the open set label shift. To be more specific, we are doing a reparameterization approach. We are extending the label shift assumption to the k+1 class, including this extra out-of-distribution class. Also, we are combining the classifier that classify ID class with the classifier that classify ID versus OD class together as the k+1 ID plus OD classifier, and then the corresponding label distribution will be a k+1 class, k+1 closed set label distribution. The structure of the model can be visualized as follows. We are given with source dataset, source labeled dataset, and then we need to generate a pseudo-OD dataset by adding Gaussian noise to the source domain data. We then have a target domain dataset, and also in terms of the classifier, we have the source domain ID classifiers, which can be obtained easily through supervised learning, and also a source domain OD classifier that can be obtained with this OD detection models proposed in the previous literature. After having this information, our model doing the open set label shift estimation model with 2 stages, and the open set label shift correction model with a single stage. Now I'll try to dive into some technical details of our work. If you are not interested, please directly take a look at the experiment section and the takeaway section. To analyze the open set label shift problem theoretically, we need 2 assumptions. First assumption is the normal open set label shift assumption that have been used in the open set label shift literature. The second assumption is our assumption on the classifier. Our assumption 2A is for the ID classifier, and assumption 2B is for the ID versus OD classifier. The following is a graphical illustration of our model. We have the left-hand side of the graphical model BS, YS, and XX, representing the random variable of ID versus OD data, the ID label, and the image. And also in the right-hand side, we have the BT, YT, and XT, representing this random variable similar on the target domain. Our OS estimation and correction pipeline can be described as follows. In our open set label shift estimation model, we first estimate the source domain label distribution C and rho S. Then we estimate the target domain label distribution pi and rho T. Finally, we adjust rho T when the classified ID-OD classifier does not satisfy our assumption. In the open set label shift correction model, we just adapt our classifier and the ID versus OD classifier for the target domain directly. In our open set label shift estimation model, we first want to estimate the source domain label distribution C for ID classes and source domain ID data ratio rho S. The source domain label distribution for ID classes can be obtained easily by just counting the frequency of the samples for each class in the source domain label data. The source domain ID versus OD ratio can be estimated with the proposed estimator in equation 2. This estimator, the error of this estimator is bounded with concentration inequalities given the assumptions and this extra out-of-distribution data set available. After obtaining the source domain label distribution C and rho S, we want to estimate the target domain label distribution rho T and pi. First, we would like to write down the negative log likelihood of this two parameter, which after our mathematical reformulation is written in the form of a k+1 closed set label shift estimation objective, where f tilde, pi tilde, and c tilde representing the k+1 classifier, k+1 label source domain label distribution and target domain label distribution respectively. After we write the objective in the mathematical form of a closed set label shift estimation objective, we can just derive an EM algorithm to obtain the maximized likelihood estimate of the target domain label distribution. Even after we obtain the target domain label distribution maximized likelihood estimate, we also propose the target domain rotate correction model under the circumstance when our assumption it may not be satisfied in practice. This assumption is for this ID versus OD classifier. To tackling this problem, we proposed this estimator rotate star hat, and bounded with the error of this estimate is bound with the concentration inequalities. This bound can be satisfied with a relaxed assumption. After having this estimate of the target domain label distribution, the source domain label distribution, and the rotate correction model, we can correct this open set label shift classifier, correct the classifier from the source domain to the target domain with this simple equation 12. We test our model with the different data set, different ID dataset plus OD dataset, and with different auto distribution detectors. As shown in this figure, our model, in terms of the estimation error, our model outperforms previous closed set label shift estimation models and open set label shift estimation model baseline. In terms of accuracy, our model also outperforms the baselines and the OpenMax open set as the classification model. As shown in this figure, our rotate correction model can gain a better estimate of the target domain rotate compared with the model that doesn't use this rotate correction approach. To summarize, if we have an open set classification problem and you are having this label shift problems, then our model can help to first estimate the test set label distribution, estimate the test set ID versus OD ratio, and finally adjust classifier to the target domain without retraining. Moreover, our model is feasible for any auto distribution detector that have been used. Our source code is publicly available at this link. If you are interested in our work, please take a look at our paper and our source code. Thank you for your listening.